In this lecture, we are going to discuss about the energy sources and its classification, network and network elements, and we'll solve some problems using mesh analysis. So first, we'll see what is energy source. So here, energy source is nothing but the voltage and current source which provide energy to the circuit or a network. Okay, it is an active source. According to the terminal voltage current characteristics, these electrical sources, that is, both the voltage and current sources, are categorized into ideal sources and practical sources. Further, they are classified into dependent and independent sources. So, first we'll see voltage source. In voltage source, we have ideal as well as practical voltage source. So, first we'll see ideal voltage source. So, ideal voltage source is nothing but the energy source which gives constant voltage across its terminal irrespective of the current flowing through its terminals. So in other words, we can say that the voltage is completely independent of the current flowing through its terminals. So if you see the circuit, this is the representation of the ideal voltage source. So it is represented as a plus and minus inside the round. It is a DC voltage source Vs, and current flowing through the circuit is Is due to the source, and this is the terminal voltage. If we connect a load over here at these two terminals, then Vt may be the voltage across the load. So this is called as a terminal voltage. Now if we draw a graph between Vs and Is, so this terminal voltage will remain constant irrespective of the increase in current value. Okay, so the characteristic curve drawn between voltage and current will remain the same for the ideal voltage source. So next we'll see what is a practical voltage source. Okay, so practical voltage source has a small internal resistance connected in series with the voltage source. So it is always represented as R suffix SC. The internal resistance is represented as R suffix SC. So due to the presence of this particular internal resistance, voltage will drop. Okay, as the current increases, the voltage will drop. Okay, this is the representation. So here the voltage source is connected in series with a smaller value of a resistance called the internal resistance. Here again Vs is the source voltage, Is is the current, and Vt is the terminal voltage. So if we draw the characteristics between Is and Vs, so this Vt will slightly droop as the current increases. Okay, this droop is because of the presence of this internal resistance. So this dotted line represents the ideal characteristics, and this is the practical characteristics. So next we'll see the current source. In current source also we have both ideal and practical. So in the case of an ideal current source, it gives a constant current at its terminals irrespective of the voltage. Okay, in other words, current is completely independent of the voltage. Okay, so this is the representation of the current, an arrow inside the circle. Okay, Is is the current flowing through the so current given by the source, and Vt is the terminal voltage. So if you see the characteristics, so this current will remain the same. So if we connect a load across these two terminals, the current will flow through the load. So load current will be IL. So IL will be equal to Is. So this will remain constant irrespective of increase in voltage Vt. Okay. So now we'll see the practical current source. So similar to the practical voltage source, this practical current source has a smaller internal resistance, but in this case it is shown as a resistance connected in parallel with the current source represented as R suffix SH. So due to the presence of this, the magnitude of the current falls even though the voltage is increased. So this is a representation, current source in parallel with the internal resistance. So now if we see the characteristics will be slightly drooping. So the current falls as the voltage increases. So the dotted line represents the ideal case. So the sources so far we have discussed are independent sources. Okay, they are completely independent of each other and are not affected by any other parts of the circuit also. Okay, so they are defined as the independent sources. So now we'll see dependent sources. Okay, dependent sources are those whose value of source is not fixed. Okay, instead it depends on the voltage or the current existing at some other location of the circuit. So here the voltage source or current source depends on any other value, that is any of the currents flowing through or voltage appearing across the terminals in any other part of the particular network or a circuit. So accordingly we have four different types. We'll see one by one. So first one is the voltage dependent voltage source. So in this case the source produces a voltage as a function of voltage elsewhere in the given circuit. So this is represented by a diamond shaped. Okay, so inside the diamond shape we have plus and minus. So previously for independent sources it is represented as round. So here it is represented as diamond. So now the voltage source value is equal to K times V1. So V1 is the voltage at any other part of a circuit. Okay, V1 is the voltage appearing across any of the resistors or any of the other elements in any part of the same circuit. Okay, so next current dependent voltage source. So here the voltage source produces a voltage as a function of current elsewhere in the given circuit. So this is a representation. Here V is given by K times I1, where I1 is current flowing through any of the elements in other part of the same circuit. Okay, so next we have voltage dependent current source. Here the current source value depends on voltage elsewhere in the given circuit. So again this is a representation. Current is equal to K times V1. V1 is nothing but the voltage across any of the elements located at any other location of the given circuit. Similarly, last one is a current dependent current source. So here current source value is expressed as a function of current only. Okay, so this current may be flowing elsewhere in the given circuit. So this is a representation. I is equal to K times I1. So now we'll discuss some of the network elements. So first we'll see what is a network. So a network, or simply an electrical network, is one which is composed of number of electrical sources connected to various circuit elements. So here we have more than one or two, more than one electrical sources will be available. So these electrical sources are connected with the various circuit elements, like it may be a resistor, inductor, or a capacitor. So now on the other hand, electric circuit is a network that has electrically active components. So here the components will be active in nature. So the energy sources are active components. Active components are nothing but the components which give energy to the circuit. Okay, such components are defined as the active components. So next, the components are joined together either in series or parallel or series parallel combination. So now we'll see what is a node. So the term node refers to a point or a junction where two or more elements are connected together. Okay, so node is nothing but a point or a junction, so wherein the elements are connected together. Similarly, we have one more term, the mesh. So the mesh is also called as a loop. Okay, so mesh or a loop is a group of branches that provide a closed path in a network in such a manner that the remaining branches do not still create a closed path if one branch is removed. So here mesh or the loop is nothing but the group of branches connected together to form a closed loop, closed path. Okay, so if you remove any one of the branches, the path will not be closed, right? So now branch is nothing but the segment of the network connecting various network elements together. Okay, so now we'll discuss mesh analysis. So there are two important techniques available in network theory, like mesh and nodal analysis. So these two are the basic important techniques used for finding the solutions for a particular network. So we can find out the values of currents, unknown values of currents using mesh analysis, and similarly unknown values of voltages using nodal analysis. So mesh analysis is very useful for the network comprising of larger number of voltage sources, and mesh analysis is used only for the planar networks. So a circuit or a network is said to be planar if it can be drawn on a plane surface without any crossovers. So there should not be any crossover in a particular circuit. So this can be easily drawn on a plane surface. Okay, such circuits are defined as the planar circuits or the network. So the mesh analysis is applicable only for such circuits. So now we'll see what are all the steps for solving the using mesh analysis. So the first step is to check whether the circuit is planar or not. So as I said earlier, the mesh analysis is applicable only for the planar network or planar circuit. So first we have to check whether the circuit is planar or not. So the second step is to select the mesh currents. So we have to always assume mesh currents. If there are two meshes, then we have to assume two unknown values of currents. Okay, so if we have three mesh, then we have to assume three currents. Okay, depending upon the number of meshes available, we have to assume the mesh currents. And finally, we have to write the Kirchhoff's voltage law equations in terms of unknown currents, and we have to solve them to find the solution. Now let us solve the problem using mesh analysis. So mesh analysis is generally used for finding out the unknown values of current. So here let us assume unknown value of current, say I1 and I2. Okay, here we have two loops or meshes. So this 25 volts 4 ohms resistor and 2 ohms resistor forms one mesh, and similarly 2 ohms 1 ohm and 5 volts resistor forms another mesh. So since we have two meshes, we have to assume two currents I1 and I2, and here we have to assume the currents in clockwise direction. Okay, always assume the currents in clockwise directions because it will minimize certain errors. Okay, so once we have assumed the currents, we have to write the mesh equations. Okay, so first we'll write the equation for mesh 1. Okay, here we have to apply Kirchhoff's voltage law. So we all know Kirchhoff's voltage law. So Kirchhoff's voltage law states that sum of the voltage rise is equal to sum of the voltage drops in a closed circuit or a closed loop. Okay, so here voltage rise is always written with respect to voltage source only. Okay, so if the assumed current direction is from negative to positive with respect to voltage source, then it is considered as voltage rise. Similarly, if the assumed current direction with respect to voltage source is from positive to negative, it is considered as voltage drop. Okay, and then voltages across all the resistors are assumed as voltage drops. Okay, so now for mesh 1 we will write both the voltage rise and voltage drops. So if you see I1, so I1 flows from negative to positive in this direction with respect to 25 volt source. So this is considered as voltage rise. Okay, so we'll write here. So this is considered as voltage rise 25. Okay, so next we have to write the voltage drop across the resistor 4 ohms. Okay, voltage drop across the 4 ohm resistor. So voltage drop is given by Ohm's law, V is equal to I into R. Here current flowing through this particular resistor is I1. Resistance value is 4. So I1 into 4 or 4 into I1. Okay, so next we have to write the voltage drop across 2 ohms resistor. So if you see here, this 2 ohms resistor lies in between mesh 1 and mesh 2. Okay, so from mesh 1 the current I1 is flowing from top to bottom, and similarly I2 in mesh 2 flows in this direction. So both the currents are in the opposite directions. So net current flowing through this 2 ohms resistor will be I1 minus I2 or I2 minus I1. Okay, so while writing for mesh 1 we have to consider them as I1 minus I2. So the resistance value is 2. So the current is I1 minus I2. So the voltage drop can be written as I1 minus I2 into 2. So or we can write it as 2 into I1 minus I2. So if we multiply 2 inside, we'll get 2I1 minus 2 I2. Okay, so we have only 3 elements. We have written all the voltage rise and voltage drops. So now we'll add all the voltage drops. So if we add all the voltage drops, we'll get 4I1 plus 2I1 minus 2I2. Okay, so this is equal to 6I1 minus 2I2. So by Kirchhoff's voltage law already we have discussed, sum of the voltage rise is equal to sum of the voltage drops. So we can equate this voltage drop to voltage rise here. Okay, so we can write 6I1 minus 2I2 is equal to 25. So this is equation number 1. Similarly, we can write the equation for mesh 2. So in mesh 2 again, we have to write voltage rise and voltage drops. So if you see here, this current I2 flows in this direction with respect to 5 volts, that is from positive to negative. So if the current is flowing from positive to negative, then it is considered as voltage drop only. So in this case, we don't have voltage rise. So we can write voltage rise is equal to 0. So this 5 volt source is considered as a voltage drop. So next we have to write the voltage drop across 2 ohms resistor as well as 1 ohm resistor. Okay, so if we consider 1 ohm, the current flowing through this 1 ohm resistor is I2 only. Okay, so the voltage drop across 1 ohm resistor can be written as 1 into I2 or simply I2. So next we have to write the voltage drop across 2 ohms resistor. So current flowing through 2 ohms is I2 minus I1. Okay, while writing for mesh 1, we have to consider the current as I2 minus I1 multiplied by 2. Okay, so if we multiply 2 inside, so we'll get 2I2 minus 2I1. So now we'll add all the voltage drops. So this is equal to 5 plus I2 plus 2I2 minus 2I1. So this is equal to minus 2I1 plus 3I2 plus 5. Okay, so now by Kirchhoff's voltage law, sum of this voltage drop will be equal to voltage rise. So we can write minus 2I1 plus 3I2 plus 5 is equal to 0, or minus 2I1 plus 3I2 is equal to minus 5. This is equation number 2. Okay, so we have only 2 meshes, so we will be having only 2 mesh equations. Okay, so now we'll write this mesh equation in the matrix form. Okay, so here the unknown values of currents are taken over here. Okay, so now we'll have to write the coefficients of I1 and I2 for equation 1 and 2. So if we take first equation, the coefficient of I1 is 6, coefficient of I2 is minus 2, and then on the right hand side we have 25. Similarly for mesh 2 equation, coefficient of I1 is minus 2, I2 is 3, and on the right hand side we have minus 5. So this is equivalent to resistance matrix multiplied by current matrix, that is equal to voltage matrix. So this is again Ohm's law. Okay, this is the resistance matrix. Okay, this one resistance matrix, current matrix, and this is the voltage matrix. So the general form of resistance matrix is given by R11, R12, R21 and R22. Okay, multiplied by unknown values of currents I1 and I2, that is equal to voltages connected across the meshes. Okay, 1 and 2. So V1 and V2. Okay, so now if we see here, this diagonal elements, that is R11 and R22. So the diagonal elements are some of the resistors in individual meshes. So if you see here, R11 is equal to 6. Okay, so 6 is nothing but 4 ohms plus 2 ohms. So in mesh 1 we have 2 resistors, that is 4 and 2. So if we add these two, we'll get 6. So R11 is the sum of the resistor sum of resistors in mesh 1. Okay, sum of resistors in mesh 1. Similarly R22, so the diagonal elements are sum of the resistors are. Okay, if you see mesh 2, we have 1 ohm resistor and 2 ohm, so adding these two we'll get 3. So R22 is again the sum of resistors in mesh 2, in mesh 2. So if you see the off diagonal elements, that is R12 will be equal to R21. So this is nothing but the common element between mesh 1 and 2, okay, with the negative sign. So this 2 ohms resistor is the common element between mesh 1 and 2. So here we have this common element with the negative sign, okay, -2, -2. So R12 is equal to R21 is the common element with the negative sign. Okay, so next we'll solve the matrix using Cramer's rule. So we'll apply Cramer's rule here. So by applying Cramer's rule, okay, for solving the unknown values of current. Okay, so the matrix, I will rewrite the matrix over here. So the matrix is 6 -2 -2 3 into I1 I2. So on the right hand side we got 25 and -5. Okay, so now we have to find out the delta value. So delta is nothing but the determinant of this resistance matrix. Okay, so 6 -2 -2 3. So the determinant value is 6 into 3 minus -2 into -2. So 18 minus 4, that is equal to 14. So next, for finding out I1, we have to find out delta I1 value. So for finding out delta I1, so here 6. Okay, so for finding out delta I1, so the first column should be replaced with the right hand side matrix. On the right hand side we have on the right hand side we have 25. So we have to replace the first column with the right hand side matrix. So that is 25 minus 5. Okay, second column will remain the same, -2 3. So again we have to find out the determinant for this delta I1. So that is 25 into 3 minus -2 into -5. So 25 into 3 75 minus of 10. So this will be equal to 65. So now I1 is given by delta I1 divided by delta. So 65 divided by 14. So on solving this we will get 4.64 ampere. Okay, this is the I1 value. So next, for finding out I2 value, we have to find out delta I2. So for finding out delta I2, we have to replace the second column of the resistance matrix. Okay, so second column is replaced by the right hand side matrix. Okay, so now we have to find out the determinant for this one also. 6 into -5 minus of -2 into 25. Okay, so 30 minus 30 plus 50. So this is equal to 20. So now I2 is given by delta I2 divided by delta. So 20 divided by 14. So this will give you 1.428 ampere. Okay, so this is the answer. So now one more thing I just want to clarify here. So here we have to specify the, so here here we have I1 and I2. So these two are the unknown values of currents. Whereas on the right hand side we have V1 and V2. Okay, so if we see the mesh 1 with respect to I1, okay, with respect to I1 direction, this is the voltage rise. As we have already discussed, if the current direction is from negative to positive, then it is considered as voltage rise. So if it is voltage rise, then we have to write it as such. Okay, write 25 as 25 only. So but in mesh 2, the assumed current direction is from positive to negative with respect to this particular voltage source. So this voltage source is considered as a voltage dropper. So we have to add minus over here. Okay, here we have to add minus. So here we have to write it as such. Okay, if it is a voltage rise, then plus. If it is voltage drop, then we have to specify it with the negative sign.